we're going to Google bidirectional brain-machine interfaces. And we're going to click on the images. Let's open up this lovely image. General functioning of a bidirectional BCI. The clockwise flow, indicated with the blue arrow, represents the neural data acquisition process, while the counterclockwise flow, represented with a red arrow, models the brain stimulation. If we're looking at the blue arrow, which represents the neural data acquisition process, we start with number 1, generation of neural activity. We have brain signals, leading us to number 2, neural data acquisition and stimulation. Here is the raw data, leading us to number 3, data processing. Here we have acquisition action, leading us to number 4, applications. And here is the user feedback, leading us back to number 1. And if we follow the red arrow, which is going counterclockwise, it's the neural stimulation. And we start with number 4, the applications. Here we have stimulation action, leading us to number 3. Then we have firing pattern, leading us to number 2. And here we have stimulation, leading us to number 1. We're going to go to ResearchGate, and we're going to read Brain-computer interfaces. Brain-computer interfaces, BCIs, have emerged as a novel technology that bridges the brain with external devices. BCIs have been developed to decode humans' intention, leading to direct brain control of a computer or device without going through the neuromuscular pathway. Bidirectional brain-computer interfaces not only allow brain control, but also open the door for modulating the central nervous system through neural interfacing. You see right here, as we just read, it says brain control. Now, why would they have all of this if they were only interested in moving cockroaches around with a remote control? We read about the cockroaches in episode 75, Engineered Biological Entity. Let's go over here to Science Direct, and we're going to read Biohybrid Approaches to Interface with the Nervous System, the Best of Both Worlds. Effective control and monitoring of the brain requires spatial, cell type, molecular, and temporal precision. Control and monitoring of the brain. Many types of devices can be utilized for control of cellular physiology with high spatiotemporal precision. Genetically encoded actuators that respond to these devices enable cell type specific control of cellular physiology. Many genetically encoded proteins do not respond to energy delivered by neuromodulatory devices. Combination of devices, materials, and genetically encoded actuators is a basis for powerful methods of neuromodulation. Synthetic materials and devices that interact with light, ultrasound, or magnetic fields can be used to modulate neural activity with high spatial and temporal precision. However, these approaches often lack the ability to target genetically defined cell types and signaling pathways. Genetically encoded proteins can be expressed to modify the host tissue and provide cellular and molecular specificity. But compared to synthetic materials, these proteins often interact weakly with externally applied energy sources. Synthetic materials can respond to optical, acoustic, and magnetic stimuli to focus, convert, and amplify forms of energy to ones that are more accessible to engineered cells and proteins. So the best way to explain this is that the air molecules next to the augmented humans are much more friendly to them. By combining the devices, synthetic materials, and genetically encoded proteins or cells, researchers can gain the ability to interface with the nervous system with improved spatiotemporal, cell type, and molecular precision. Here we review recent advances in the biohybrid approaches that use optical, acoustic, and magnetic energy sources. The nervous system has incredible complexity across a multitude of spatial and temporal scales. Neural circuits are composed of multiple cell types, each of which are complex biological entities that communicate with their environment through multiple means and on multiple timescales ranging from milliseconds to years. Consequently, to effectively interface with the brain, one needs to employ methods that work with spatial, temporal, cell type, and molecular precision. Materials and devices can be designed to deliver energy to neural tissue with high temporal precision that can exceed the millisecond to hour timescales of cellular signaling. However, such energy, for example, light, heat, electrical fields, magnetic field, or ultrasound, often cannot control genetically defined cell populations or signaling pathways, which is necessary for understanding of neural circuitry. On the other hand, biology-based approaches, such as genetically encoded actuators of cellular physiology, can selectively respond to various forms of energy with sensitivity that is improved compared to proteins naturally existing in the brain. Consequently, such actuators can be selectively controlled with the devices, thus enabling genetically defined control of the cells in the brain that express the actuator. While this approach has been effective in many cases, such as optogenetics or sonogenetics, these approaches do suffer limitations when the deposited energy is attenuated, unfocused, or otherwise incapable to actuate an engineered proteins. To broaden the range of applications where devices and genetically encoded actuators can be used to control cellular physiology, researchers begun to incorporate material components, such as micro or nanoparticles, that amplify, focus, or convert energy to make it more readily accessible to the genetically encoded actuators. When the three components, devices, biomaterials, and engineered proteins are combined together, they form biohybrids. Such biohybrids exhibit spatial-temporal precision of electronic devices and molecular and cell-type specificity of biological approaches in a wide range of applications. Here, we will discuss such biohybrid approaches and their advantages for controlling cellular physiology in the nervous system. Hybrid optogenetics. By using materials that can convert long wavelength photons to shorter wavelength photons, heat, electric fields, or ultrasound waves, hybrid optogenetics, one can achieve optical modulation of neural activity with increased optical penetration depths. Acoustic control of brain physiology. Ultrasound can safely deliver energy to the brain through an intact skull, making it an attractive form of energy for interacting with brain cells. The mechanical forces of ultrasound can then be used to actuate cellular physiology, enable localized delivery of molecules, elicit conversion to other forms of energy such as light, or be dissipated as heat. Utilization of each of these forms of energy could be improved with the use of synthetic materials. Magnetogenetics. While several groups have reported that cells can be genetically modified to respond to magnetic fields, these results have been questioned because of the biogenic nanoparticles that result from this genetic manipulation have extremely weak magnetic properties, and several groups have failed to produce certain aspects of this work. Reports of magnetogenetics have been based on genetic expression or manipulation of the iron, protein, ferritin that naturally forms a roughly 8 nanometer iron. Shape shifting is actually natural to humans, but they wanted to get their hands on it so that they could create creatures like Rob the Ebi, the engineered biological entity. And they just didn't tell anybody that. They kept telling everyone that it's aliens. It's not aliens, it's engineered biological entities for wireless tissue engineering. No, really, I'm serious. Let's Google. Synthetic biology circuits can respond within seconds. And let's click on this lovely image here. This is from MIT. MIT engineers designed the first synthetic circuit that consists entirely of vast, reversible, protein-to-protein interactions. And this was on July 1st, 2021. Synthetic biology offers a way to engineer cells to perform novel functions, such as glowing with fluorescent light when they detect certain chemicals. Usually, this is done by altering cells, so they express genes that can be triggered by a certain input. I will leave the link in the description for those who want to read this MIT research paper. But for now, let's go over here to ResearchGate. EEG-based brain-computer interfaces, BCIs, a survey of recent studies on signal sensing technologies and computational intelligence approaches and their applications. The first research papers on brain-computer interfaces, BCIs, were released in the 1970s. In the 1970s. So this has been around for over 50 years. Let's take a look at this image. Figure 2. BCI contributes to various fields of research. And here are the applications of brain-computer interfaces. We have game interaction, robot control, emotion, fatigue, sleep quality, and clinical trials. Now let's hop on over here to the Frontiers Journal. Current status, challenges, and possible solutions of EEG-based brain-computer interface, a comprehensive review. Brain-computer interface, BCI, in essence, aims at controlling different assistive devices through the utilization of brainwaves. It is worth noting that the application of BCI is not limited to medical applications, and hence, research in this field has gained due attention. Moreover, the significant number of related publications over the past 2 decades further indicates the consistent improvements and breakthroughs that have been made in this particular field. So again, related publications over the past 2 decades. Nonetheless, it is also worth mentioning that with these improvements, new challenges are consistently discovered. This article provides a comprehensive review of the state of the art of a complete BCI system. First, a brief overview of EEG-based BCI systems is given. Secondly, a considerable number of popular BCI applications are reviewed in terms of electrophysiological control signals, feature extraction, classification algorithms, and performance evaluation metrics. Finally, the challenges to the recent BCI systems are discussed, and possible solutions to mitigate the issues are recommended. Communication, or social interaction, is one of the key principles of human civilization. This quality enables one to share emotions, expectations, and creative thoughts amongst human beings. In the event that this communication is established through speech, gesture, or writing, human communication becomes easier and devoid constraints. Nonetheless, people who are suffering from locked-in syndrome do not have the aforementioned options of interaction. Patients with locked-in syndrome could not interact or express themselves, although they are well cognizant of things around them. ALS, cerebral palsy, brainstem stroke, multiple sclerosis, cerebral palsy, and spinal cord injuries are the main causes of locked-in syndrome. It is almost impossible for a person who is affected with the locked-in syndrome to communicate with other persons, and hence, brain-computer interface is a promising means to furnish them with basic communication abilities. Fundamentally, the human brain and devices are interfaced through the concept of BCI, in which the users will have to generate a variety of brain waves that will be recognized and converted into commands to the devices. In its earlier days, researchers intended to use this technology to develop assistive devices for medical purposes only. Nonetheless, the employment of this technology has expanded, and it has found its way into non-medical applications. It is discernible that over the last 15 years, a considerable amount of original articles, as well as reviews, have been published on BCI. An excellent review article on BCI spelling systems was published in 2018, giving a concise description of some successful recent BCI spelling models, including their categories, methodologies, and results. The authors also listed some limitations of current systems, as well as making recommendations for directions that could be pursued to overcome the issues. However, it is worth mentioning that the content of the review emphasized and was restricted to only BCI spellers. There are other noticeable BCI reviews that cater to specific applications. For instance, wheelchair control, BCI mobile robot, emotion recognition using EEG, biometrics, and virtual reality and gaming. See, here's your virtual reality and gaming. Essential components of BCI technology. Brain-computer interface. BCI is an effective as well as powerful tool for user-system communication. Through this system, from the issuance of the commands to the completion of the interaction, no external devices or muscle intervention is required. Nicholas and Gomez define brain-computer interface or brain-machine interface as a hardware and software communication strategy that empowers humans to interact with their surroundings, with no inclusion of peripheral nerves or muscles, by utilizing control signals produced by electroencephalographic activity. Every BCI system essentially consists of 5 components: brain activity measurement, pre-processing, feature extraction, classification, and translation into a command. Figure 1 depicts a typical block diagram that illustrates the different stages of EEG signal processing for BCI. In the brain activity acquisition phase, the brain activity from the targeted user is captured through the various types of EEG sensors. The raw EEG data includes a variety of artifacts, and these artifacts are eliminated in the pre-processing phase. Feature extraction aims at describing the signals by a few relevant values called quote-unquote features. Often, at this stage, the selection of significant features is also investigated. The extracted features are then classified through different machine learning and deep learning algorithms in the classification phase. Finally, the classified outcomes are translated into device commands and develop real-life BCI application. And here is Figure 1, General Architecture of a Brain-Computer Interface. We start with the human and the brain, which has signal acquisition. Here it says pre-processing, your feature extraction, classification, device command, and BCI application. I will leave the link in the description for those who want to read this entire article. But for now, we're going to go over here to ResearchGate. And we're going to read Towards Brain-Computer Interfaces for Drone Swarm Control. Non-invasive brain-computer interface decodes brain signals to understand user intention. Recent advances have been developed for BCI-based drone control system as the demand for drone control increases. Especially, drone swarm control based on brain signals could provide various industries such as military service or industry disaster. This paper presents a prototype of a brain swarm interface system for a variety of scenarios using a visual imagery paradigm. We designed the experimental environment that could acquire brain signals under a drone swarm control simulator environment. Through the system, we collected the EEG signals with respect to 4 different scenarios. 7 subjects participated in our experiment and evaluated classification performances using the basic machine learning algorithm. The grand average classification accuracy is higher than the chance level accuracy. Hence, we could confirm the feasibility of the drone swarm control system based on EEG signals for performing high-level tasks. And let's look at this lovely image. So in the military, they use brainwaves to control drones. We're going to go over here, and we're going to Google the Cognitive Technology Threat Warning System. And let's click on the Wikipedia link. The Cognitive Technology Threat Warning System, otherwise known as CT2WS, is a brain-computer interface designed to analyze sensory data and then alert foot soldiers to any possible threats, passive or direct. As I just said, they are using the BCI in the military for their soldiers. Now over here to ResearchGate. Mitigating and responding to cognitive warfare. For NATO to have the capability to acquire and preserve decision and cognitive superiority over their adversaries and across the conflict spectrum, scientific-based knowledge is needed to support and increase NATO's operational readiness to respond to COG war. COG war is not necessarily new, but has emerged as a product of integration and confluence of many technological advances, and as availability and access to information and technology has increased. COG war takes well-known methods within warfare to a new level by attempting to alter and shape the way humans think, react, and make decisions. COG war has emerged replete with security challenges due to its invasive, intrusive, and invisible nature, and where the goal is to exploit facets of cognition to disrupt, undermine, influence, or modify human decisions. COG war represents the convergence of a wide range of advanced technologies, along with human factors and systems, such as artificial intelligence, AI, machine learning, information communication technologies, neuroscience, biotechnology, and human enhancement that are being deliberately used by NATO's adversaries in the 21st century battle space. COG war presents a significant risk to global defense and security at every level, including economic, geopolitical, social, cultural, as well as threatening human decision-making. The task of ET356 was focused solely on identifying and suggesting defense S and T to strengthen the alliance's deterrence against COG war and improve NATO's and national resilience critical to NATO's core task to safeguard allied nations, societies, and shared values. COG war gives rise to the adversary's ability to shape human cognition, perception, sense-making, situational awareness, and decision-making at all levels. The ability to intentionally misuse information within digital networks and disseminate it globally is the risk. So for those who are confused, cognitive war is mind control. As we just read here, to alter and shape the way humans think, react, and make decisions. This is mind control at its finest. We're going to Google cognitive warfare, a battle for the brain. And we're going to click on this link. This is NATO's official website. Let's watch this quick video.
We've heard Russian officials say that they have no intention of invading Ukraine. In fact, Minister Lavrov repeated that to me today.
You know, it was not us who abandoned all contacts.
So he was not there to listen to the others and to discuss and participate in a meeting. And everybody was asking, mainly to Russia, who is the aggressor, to stop this war.
Nausea? Yes. Headaches? Yes. Blurred vision? Yes. Balance and memory issues? Yes. Are you suffering? Yes.
Why there are not new disinformation campaigns, fake news, or conspiracy theories are used to fragment states and polarize the public opinion.
We have been attacked, there has been deceptions, and there has been disinformation throughout the history of NATO.
It's about relationship between NATO and EU.
Various external actors are trying to undermine the unity of the alliance and affect our populations.
When anybody preaches disunity, tries to pit one of us against the other through class warfare, race hatred, or religious intolerance, you know that person seeks to rob us of our freedom and destroy our very lives.
Cognitive warfare is not the means by which we fight, it is the fight itself. The brain is both the target and the weapon in the fight for cognitive superiority. Contesting in this environment comprises deliberate, synchronized military and non-military activities throughout the continuum of competition designed to gain, maintain, and protect cognitive advantage. Cognitive warfare focuses on attacking and degrading rationality, which can lead to the exploitation of vulnerabilities and systematic weakening. However, this becomes increasingly complex as non-military targets are involved. An example, Russian social media and public information operations targeted much of the international community in an attempt to label Ukraine as being at fault. Through a combination of communication technologies, fake news stories, and perception manipulation, Russia aims to influence public opinion as well as decay public trust towards open information sources. These narratives have extensive reach and often involve both offensive and defensive posturing. China, as a strategic competitor for NATO, describes cognitive warfare as the use of public opinion, psychological operations, and legal influence to achieve victory. Combat psychology has significant impact on the warfighter's ability to function. Intelligent Psychological Monitoring System, a recent smart sensor bracelets developed by China, focuses on recording facial information, emotional changes, and psychological states of soldiers to determine their combat status. Outside of the battlefield, influence can also affect law, rule of order, and civil constructs. This inclusion of quote-unquote lawfare and the targeting of broader community sentiment has significant impact, since so many civilians and non-combatants are potentially exposed. Allied Command Transformation manages the cognitive warfare exploratory concept, which is part of the larger warfare development agenda. Synchronization of adversarial effects against emotional and subconscious domains are increasing. Understanding frameworks, definitions, impacts, and risks enables better political decision-making, military capability development, and overall alliance-wide security. Allied Command Transformation educates, collaborates, protects, and shapes NATO forces on the topic of cognitive warfare, providing guidance on awareness, civil-military cooperation, societal resilience, and data sharing for the alliance's current and future security considerations. Now, let's go over here to Medical Design Briefs. This was released on May 23, 2019. Battelle to develop injectable bidirectional brain-computer interface. And let's look at this lovely image. So it's injectable. It has decode and encode for fMRI and EEG. They can write to your neurons. Battelle has for years successfully demonstrated brain-computer interface projects. Just look at Neurolife, which has enabled a quadriplegic man to move his hand again using his thoughts. Now, the government's forward-thinking Defense Advanced Research Project Agency, DARPA, has awarded a contract to a Battelle-led team that pushes researchers into the realm of what was once considered science fiction. Imagine this. A soldier puts on a helmet and uses his or her thoughts alone to control multiple unmanned vehicles or a bomb disposal robot. That's the basis for this effort for DARPA's next generation non-surgical neurotechnology N3 program. The N3 program seeks development of high-performance bidirectional brain-machine interfaces for able-bodied service members. Most of the current BCI research, including Battelle's Neurolife technology, focuses on helping people with disabilities who must undergo invasive implant procedures, including brain surgery, to enable a BCI that can restore lost function. For the next BCI leap, in which the technology can be used by healthy military service members, it's imperative to find lower risk and less invasive options. It's a path Battelle's senior research scientist, Sharma, has already begun to navigate. Heavily involved for years with the Neurolife project, Sharma began to develop ideas for non-surgical BCI options. The DARPA N3 program provides the opportunity to further develop them. Welcome to DARPA's non-invasive DARPA N3, which we learned about in the previous episode, episode 76. Battelle's N3 concept for a minimally invasive neural interface system called BrainStorms, brain system to transmit or receive magnetoelectric signals, involves the development of a novel nanotransducer that could be temporarily introduced into the body via injection and then directed to a specific area of the brain to help complete a task through communication with a helmet-based transceiver. Upon completion, the nanotransducer will be magnetically guided out of the brain and into the bloodstream to be processed out of the body. Wonderful! Inject some magnets into the body that you are remotely piloting through the brain, but don't tell who you're working on. That way they can test that out on people for themselves.